Okay, today's lecture is on limiting reactants and percent yield. This is also known as adjusting to reality. Or as the kids like to call it, keeping it 100, right? Okay, so, right, but this is, so what happens with our actual, when we do a chemical reaction, we don't actually have exact amounts of products that are going to give us even amounts of, exact amount of reactants are going to give us equal, even amounts of products. Okay, that went dark pretty quick. So in real life, we never have exactly the right amount IRL in real life. I can't believe that I spend more time on social media than you. All right. Exactly the right amount of reactants to completely Okay, so in real life, we never have exactly the right amount of reactants to completely use all of them up. Right? We'll use all of one of the reactants up, but we're not going to use all of them up. Okay, we will have some that are left over. Okay, there's always some reactant that runs out first. Yes. Say the whole sentence out loud to yourself, and it'll make sense. Okay. There is always some reactant that runs out first. There's always some reactant that runs out first in a reaction. The reaction will go, then one of our reactants will run out, and then we're done. We can't do anymore. So like the simulation we did yesterday when we're making sandwiches, okay, if we ran out of cheese, we can't make any more sandwiches the way that we defined what a sandwich is. Okay, we can make other kinds of sandwiches if we redefine what it is, but then that could change. You get the point. Okay, so this reactant, okay, this reactant, the one that runs out first, is called the limiting reactant. Okay, it is called the limiting reactant because it defines the end of the reaction. Okay, and the amounts of product produced. Okay, so hopefully you found in your simulation that you would have a whole plethora of molecules that you're starting with, and you had to figure out how many molecules would actually be produced, and then how many things would be left over, right? From what you started with. And you could only produce so many because you were limited by one of your reactants. That reactant is your limiting reactant. Okay, so here's our example. And we're going to work through this one together. So, all right, so for the balanced equation shown below, if we have 88 grams of C7H6 and 196 grams of O2, how many grams of water would be produced? And here is our, this is our balanced chemical equation. So, here's where we start. 1. Oh, that's off the page. 1. Okay, the first thing we do is we identify the mole ratio from our chemical equation. So if we're looking for C7H16, here, okay, and we're looking for oxygen, so we have 88 grams, right? So we have 88 grams of C7H16, which is actually heptane, okay, is one of our reactants, and the other one is 196 grams of oxygen. So what is the mole ratio then of our reactants? Well, we look at our equation, right? And it's 11 moles of O2 to 1 mole of C7H16. You guys see that? From the balanced equation. Okay, so this is our mole ratio. Okay, that's our mole ratio from the equation. Our second step, okay, is find the actual mole ratio that we have, the amount of moles of the actual stuff we're dealing with. Okay, so in other words, we have 88 grams of heptane and 196 grams of oxygen, and we need to convert those into moles to figure out what that mole ratio is. So, if we've got 196 grams of O2, and we have, I'm sliding down here, aren't I? 196 grams of O2, and 88 grams of C7H16. Yeah? How many moles do we have? So we're going to figure out our number of moles. And O2 is 32 grams per mole. Grams of O2 per 1 mole of O2. And then, so that'll tell us how many moles we have. Yeah? And so 196 divided by 32 is, I don't know offhand. So we plug that into our calculator, or we can just do it by hand, but I don't feel like doing it by hand. And we get 6.125 moles of O2. And we're losing that data a little bit behind the question. Okay, for the other one, 88 grams of C7H16. We have to find its number of moles. Okay, C7H16, that's going to be 7 times 12 is 84, plus 16 times 1 equals 16, equals, oh, check that out, 100. Mm-hmm. Okay, equals 1 mole of C7H16. Okay, this equals 0.88 mole. Right? 88 divided by 100. Okay. So, 0.8 mole, 88 moles of C7H16. Okay, we can't just go with this. We can't just say, oh, well, there's less moles of C7H16, because according to our mole ratio up here, okay, that we need 11 moles of oxygen for every 1 mole of C7H16, right? So we find a new ratio. We find the actual ratio of the reactants. Up here we did 11 to 1. We put oxygen on top and ethane on the bottom. So here we need to put oxygen on top. Okay, 6.125 moles of O2, and we're going to divide it by 0.88 moles of C7H16. And that comes out to, divide that by 0.88, and we get 6.96 is that ratio. How does this value compare to that value? This is 11, right? 11 divided by 1? That's 6.96 over 1. This is how much oxygen we have compared to our heptane. This is how much oxygen we need compared to our heptane, right? So, because this one is less and this is the actual ratio, we don't have enough for what we need. That means that oxygen is our limiting reactant. Okay, so we don't Okay, so it is the limiting reactant. Yeah? Okay, so once we have that, that then becomes, okay, that becomes the nope. Okay, that becomes the amount that we use for the rest of the stoichiometry problem. So that was 6.96. No, not 6.96. This number of moles of oxygen is how much we have. This now is what we use to finish the stoichiometry problem. So now we go and answer the question, how many moles of H2O would be produced? Well, we know that 11 moles of O2 would produce 8 moles of H2O. All right, and we're looking for grams, and so we would, I'll move this down a little bit, times, because I asked you guys to memorize this, 1 mole of H2O is how many grams? 18 grams of H2O. And then we multiply out from there. 6.125 times 18. Okay. And so this times that. I don't know, that doesn't show up very well. So 6.125 times 8 times 18 divided by 11 equals 80.18 grams of H2O. All right, so this is the catch. Once you determine what your limiting reactant is, that is the value that you do the rest of the stoichiometry from. Which brings us to the next part of the lecture. So you are going to go away. Next part of the lecture is this. Perform. When you perform this experiment in lab, you actually get produce only 68.9 grams of water. I'm making this number up. I'm just saying you do this in lab, and when you measure how much you actually have, you only have 68.9 grams of water. What is your percent yield? Okay. In other words, what percent of what you should have got did you actually get? Okay. And this is really straightforward if we're understanding our percent. Okay, it's what we actually got. Okay, so the amount on hand that you actually have divided by what we expected to get times 100% for those of you that forget to do that. And that equals your percent yield. So in this case, it would be 68.9 grams of water divided by 80.2 grams of water. And that would equal this equals 0.859, but then we multiply by 100, which leads us to 85.9% yield. And that's percent yield. Okay. Percent yield is pretty straightforward. Okay, so that was limiting reactant and how we use limiting reactant, and it was percent yield. I do want to go back to one thing on limiting reactant. What if this value, right, or let's say our mole ratio down here was, instead of 11 to 1, it was 11 to 2. What would this ratio be? 11 to 2 has a decimal equivalent of what? 5.5, right? So that would be 5.5 rather than 11. This number all of a sudden would be greater than that, right? So what would that tell us? Okay, that we have more oxygen than we need, and so the other one would be the limiting reactant. Yeah? So if our ratio of what we actually are using is greater than this, then what we have on top is in excess, and the one on bottom is the limiting. If this ratio is less, like it was for 11 over 1, and this is 6.9, then the one on top is the limiting reactant. Okay? So please use your units, and it's going to take a little bit of logic, so you need to pay attention to which number is going where. But as long as you're paying attention to that, you should be able to accomplish this. Okay? And